Hi, everyone, and welcome to the next lesson in chemistry. We're getting close to the end of this unit. We have this topic and one more, and then we'll be headed into a summative assessment and finishing off the unit. So we're making really good progress. Today we're going to continue on with stoichiometry, doing something called the limiting reactant, but really it's the third step in our understanding of stoichiometry. And I'd just like to define a couple of terms that are going to be really important today. And one of them, obviously, is the limiting reactant, and the other is the excess reactant. Because I think it's important to keep these in mind as we do these lessons. So the limiting reactant is the reactant that runs out first. And therefore limits the reaction. So it's the one that stops us from the reaction continuing. So it's the reactant that runs out first. The excess reactant is the reactant that remains after the reaction is done. So it's rare that you'd ever have the exact amount of each of your reactants so that they both run out at the same time. What tends to happen is one of them will be the limiting reactant and one of them will be the excess reactant. Now, obviously, in the case of a decomposition reaction where there's only one reactant, you don't have this problem. But in most chemical reactions where you have two or more reactants, one of them is going to run out and then the other ones will be left there. Okay, so that's what we're going to be talking about today, is how do we figure out which one is the limiting reactant, and then how do we use it. I want to go back to the analogy just to help you guys to understand this. And I'm going to use the same one as yesterday. We talked about using this car analogy as our reaction. And I know, again, it was written backwards. And so this idea that your reactants here are the wheels, the engine, the body, and the bumpers. And when those react together, they can make a car. Well, obviously, not react, but when you combine them, they make a car. And so yesterday we used the analogy to show this idea that we can't use the mass of parts to determine how many cars you're going to make, because before you do that, you've got to convert a mass to a count. And so that was yesterday's class. But I also want you to consider now is, just by looking at the masses, do we know what mass is limiting? In other words, which of these parts is going to limit the number of cars that we can build? And of course you can't. You can't, because you don't know how many parts you have. Like, one person could say, well, you have the lowest mass of bumpers. You only have 44,860 pounds of bumpers. And so therefore that's probably limiting. Well, that's not a very good way of doing it, because even though you only have a low mass of bumpers, the bumpers may not weigh very much, and so you may have lots of them. So you just have to be careful. But certainly by looking at this, we don't know what's limiting yet. The other thing to consider is that you may have a very high mass of wheels, but remember that every car uses 4 wheels, and so you've got to consider the rate at which the parts are used. And so that's another thing that you have to consider when you're considering limiting reactants. Okay, well, let's look at the data from yesterday. And so the first thing we did was we converted all of our masses to numbers. And so each of the wheels weighed 20 pounds, and so then you converted it by dividing, and we had 320 wheels. Each engine is very heavy, so each of them weighs 600, so you have 163 engines. And then each body was 300, so you had 82 bodies. And each bumper was 30, and so you had 162 bumpers. So again, this we've done the first conversion, which is to convert it to a count. And so you may say, well, what's limiting us here? And so again, the untrained person may say, well, oh no, I'm going to go with the lowest quantity of parts. And it's 82, so it must be the bodies that limit us. But we knew that you then had to divide by the number used. So you have to divide the wheels by 4, divide the engines by 1, divide the bodies by 1, and divide the bumpers by 2. And sure enough, it turns out that the bumpers were the limiting reactant. So in this analogy, the bumpers limit us, okay? And they limit how many cars that we can build. Technically, all of these other parts, the wheels, the engines, and the body, are all excess. In other words, you're going to have some of them left over at the end. Okay? So that's kind of a really good analogy for what we're doing today. So I want you to consider two things then as you do these limiting reactant questions. First and foremost is this convert to moles. Now we know that that's one of our steps in stoichiometry, so the nice thing is that when you're trying to finish or figure out the limiting reactant, the fact that you have to convert to moles is going to be useful for your next step anyway. So that conversion to moles is critical because you need a count. Okay, you cannot determine what's limiting based on a mass. You need a count. But the other thing to consider are the coefficients. So you need to consider what I'll call the rate at which the reactants are used. At which the reactants are used. Okay, well, let me take you through this with a little example here, and then we'll do a few more examples. But let's take a look at this equation. So here it is. We've got a chemical reaction where we've got this carbon compound here and this nitrogen oxide. This carbon compound looks like it's probably propene. And again, you wouldn't have to know the name of it, but anyway, C3H6. So if I told you that in this reaction you had 60 grams of this first substance and you had 50 grams of this second substance, and I said to you, which is the limiting reactant? Well, the untrained chemist might turn to you immediately and say, well, this one is the limiting reaction limiting reactant because you have less of it. And you would say to them, well, hold up a second here. We can't compare masses. We first have to convert to moles. And so here you go. You would quickly get out your periodic table and your paper and pencil, and you'd say, well, the number of moles I have of this one is I use little m over big M. Now I've already gone and looked these up, so it's going to be 60, and I've done the molar mass of C3H6, and it's 42.09. Okay, and so when I divide those, I figure out that I have the number of moles of 1.43. And I'd do the same thing again here. I'd go, well, the number of moles I have here is 50 divided by the molar mass of nitrogen oxide. And I used my periodic table and determined it to be 30.01 grams per mole. And so here I get 1.67 moles. Okay, so as a good chemist, you've converted to moles. Okay, so that was this step right up here. And now you say, and so you're, let's say you're turning, the friend who had asked you, the friend goes, oh, okay, so you've converted to moles, so therefore this one has less moles, so it's the limiting reactant. And at that point, you say, whoa, 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 whoa. Well, actually, we've only considered one of the important things because we also have to consider the coefficients from the chemical reaction because these reactants get used up at different rates. And that's what really this 4 and this 6 mean, is that 4 of these react with 6 of these. So does everyone see that really the nitrogen monoxide is being used up faster? Because if you think about it, 4 of this first one will disappear and 6 of this second one will disappear, as they convert into products. So the second thing we've got to consider, and I'm going to change colors here, is that the second thing we've got to consider is, well, I need to divide, in order to compare them, I need to divide by those coefficients. So I need to take this number of moles that I calculated first, and then I've got to divide by the coefficient. Okay, and that's going to tell me, that's going to equalize. What really I'm doing here is I'm saying, what is the weighted usage of these two? And I'm going to do the same thing here. I'm going to do 1.67, and I'm going to divide by 6. So look at this. You're using this 6 and the 4 down here to compare them, really to compare them on equal levels. So when I do that, when I divide 1.43 by 4, I get 0.3575. And when I do it here, I get 0.278. And so whichever one of those is the smallest is the limiting. It's the limiting reactant. So interestingly enough, our untrained chemists did actually guess at the correct one, but we can see that it was just by luck that they got that, because it's actually, you got to consider the two different things here. You've got to consider first, you got to convert everything to a count because everything has a different mass. And secondly, you've got to consider how fast they're used up. Because the nitrogen monoxide gets used up faster, it's got a higher coefficient, you've got to consider that by dividing each of your counts by the coefficient to get these last two numbers. And whichever one of those is the lowest is the limiting. And I'll just put a little star here, lowest number. Okay. Well, let's try this in a question. Oh, sorry, before we do, so this is just a summary of that. The two steps to determining the limiting reactant are 1, convert everything to moles in order to compare counts, and then 2, consider the different amounts used by dividing all moles by the coefficients from the balanced chemical equation. So that's kind of a summary of what we're doing here. Okay, let's try a few examples these are very similar to homework questions that you'll be doing, and I tried to pick some hard ones. So this first one says, hydrogen fluoride is a highly toxic gas. It is produced by the double displacement reaction of calcium fluoride with concentrated sulfuric acid. Determine the limiting reactant when 10 grams of the calcium fluoride reacts with 15.5 grams of the sulfuric acid. So look at this. Right now, I'm just, instead of redrawing that chemical equation, I'm going to tell you that you've got 10 grams of this one, and you've got 15.5 grams of the sulfuric acid. So again, the untrained chemist might say, well, the calcium fluoride is going to be your limiting because you have less of it. But you say, wait a second, I've got to do a couple of things here first. So the first thing you're going to do is, to determine which is limiting, you're going to convert them to moles. You're going to convert our mass to a count. Now, I've gone and done my calculations already. You could turn to your periodic table and figure out the molar mass of calcium fluoride. I've done this already, and I got 78.08 grams per mole. That's right from the periodic table. So I'm going to divide this by 78.08. So you take your calculator, 10 divided by 78.08, and so that turns out to be 0.128 moles. Here, the number of moles of my sulfuric acid is 15.5 divided by, and again, I went, you would go to your margin and calculate your molar mass of H2SO4. I calculated it already and got 98.09 grams per mole. So I divide by 98.09. So 15.5 divided by 98.09. And I get 0.158 moles. So now, that's the first thing to consider. The second thing to consider is how fast they get used up. Well, this one's a nice one because these get used up at the same rate. They both have a 1 out front of them. I know it's not written there, but we know it's there. They both have a 1, so if they have the same coefficient, they get used at the same rate. And so we don't have to worry about dividing these by anything. And so sure enough, we can just take the smallest number of moles. And so it turns out that the calcium fluoride is limiting. Now, at this point, we're done. We don't have to go on to our other steps of stoichiometry because the question simply was determine which one is limiting. And we've done that. All right, let's try another one here. This one says 3.76 grams of zinc reacts with, this number of molecules of hydrogen chloride. Which reactant is present in excess? So which one is going to be left over when we're done? Well, I picked this example because in this case, they didn't give you the equation, but we need it in order to consider that second part of the limiting reactant. So let's write this equation. So we've got zinc, and zinc can exist on its own, so it's just Zn, plus hydrogen chloride is HCl. And I know that using my activity series that the zinc will knock out the hydrogen, so it's going to make zinc chloride, but it's because of their charges, this one is a +2 charge, this one's a -1 charge, so I got a crisscross. And also I know that when hydrogen is on its own, it got knocked out, it's H2 gas. Okay, so there it is. There's my chemical equation. Let me quickly balance it. It's usually easy. Sure enough, it's just a 2 there and a 1 there. Okay, so just remember that sometimes you may have to write chemical equations. Now I've been told that I've got a mass of 3.76 grams here, and I'm being told I've got a capital N, or the number of molecules is 8.93 times 10 to the 23 molecules of the HCl. Okay, well, I need to determine which one is limiting. So the first thing I'm going to do is I'm going to convert them both to moles. So N is equal to 3.76 divided by the molar mass of zinc, which is 65.39. And so the number of moles of zinc I have there is 0.0575 moles. Okay, and here the number of moles I have here is capital N over NA. Remember, there's different ways of converting to moles. This is one of our other formulas that we have. So it's 8.93 times 10 to the 23 divided by 6.02 times 10 to the 23. And when I do that calculation, I get 1.48 moles. Okay, so just in terms, I've converted them to counts. And the important thing here is some of you may say, well, Mr. Webster, you already had a count up with the capital N, but I've converted them to counts that are comparable. If they're both in moles, then I can compare them. It's like dozens. Okay, so clearly when I look at this, I would say that this is my lowest number of moles. But remember, we have to consider the coefficients. And so I'm going to do part 2 of my limiting reactant, is I am going to say, well, I've got to divide these both by the coefficient. And so 0.0575 divided by 1, well, that's easy. It's just 0.0575. But here I've got to do 1.48 divided by 2, and you get 0.74. So even after dividing them, the 0.0575 is smaller, and so it's the limiting reactant. So the limiting reactant was the zinc. Is the zinc. Okay, so that's kind of, these questions just said which one, oh, sorry, it said which one is excess, so my apologies. And so I would say this one, I would say the HCl is the excess reactant. The HCl is the excess reactant because it's larger, which means it's going to be left over. Some of it's going to be left over at the end. Okay. Here's another one. So this one's a bit more, this is a very complicated problem, and so I thought this would be a good one to finish off. It covers a lot of things. So here we go. It says hydrazine reacts exothermically, which means it gives off heat, with hydrogen peroxide. Now it says 120 grams of the hydrazine reacts with an equal mass of the hydrogen peroxide, which is the limiting reactant. So for part A, it's really what this lesson was about. It's to figure out which is limiting. Okay, so let's do that first. I'm going to rewrite my equation. Plus 7H2O2 makes 2HNO3 plus 8H2O. Okay, so the mass we have here is 120 grams. The mass, they said you have an equal mass of the hydrogen peroxide. Okay, so that's technically what we've been given. To start off with, we want to figure out which is limiting. Okay, so here we go. Let's start by converting them both to moles. So it's going to be 120. Now I've already gone and looked up the molar mass of N2H4. And just to save me a little bit of time, it's 92.02 grams per mole. Okay, so here we go. It's 120 divided by 92.02. And so you get 1.30 moles. Okay, and here the number of moles here is 120 divided by 34.02. So 120 divided by 34.02, you get 3.53 moles. Okay, so again, at this point, we've only done the first step of finding the limiting reactant, because we have to now consider the coefficients, because obviously the hydrogen peroxide gets used up a lot faster. Every time one molecule of the N2H4 disappears, 7 of the H2O2 disappear. So for part 2 of limiting reactant, we're going to divide this by 1, and we're going to divide this one by 7. And when we do that, we get obviously 1.3 here, but 3.53 divided by 7 is, you get 0.504. So clearly, this is the lower of the two numbers as we compare these. So therefore, the hydrogen peroxide is limiting. Okay. So we've answered part A, the H2O2 is limiting. Okay. B, it says what mass of the HNO3 is expected? Now this is where we're going to now continue with our steps of stoichiometry. So technically what they're asking us for is, I'm going to put a question mark here because they want to know what mass we're dealing with. So think back to the steps of stoichiometry. So technically, we have done step number 1, and I'm going to put a little check mark there to it's like a verification. I've written my balanced equation, and I've written down what I've been given. But the fact that we've figured out the limiting reactant means that we've actually also done step number 2 of stoichiometry, which was to convert to moles. Now, one thing I'm going to show you is that we're only interested in the limiting reactant. So look what I'm going to do is I'm actually going to put an X through all this because I don't need it. It's the N2H4 is excess. It's not going to stop me. I only need to worry about the H2O2. Now, one other thing I'm going to show you is that I want to go back to that 3.53. That's the number of moles that I'm concerned with. Okay, so now I'm going to do step 3 of stoichiometry, which is my mole ratio. And I'm going to do H2O2 to HNO3, so my limiting reactant to the one that I'm interested in. Okay, from my balanced equation, I know that it's a 7:2 ratio. And I know I've been given 3.53 moles of H2O2, and I need to solve for X. So now we need to cross multiply this and solve for X. So 7X is equal to 2 times 3.53. Okay, and so divide by 7, and so the number of moles of the HNO3 is going to be 2 times 3.53 divided by 7, so it's roughly 1 mole. Okay, that's cool. That's a nice number to work with, because look at this now. Our step 4 is to convert back, and these are the 4 steps of stoichiometry that we learned yesterday. Convert back to whatever's required. Well, they asked for a mass, and so it's going to be N times capital M. And so I need to go look up the molar mass of the HNO3, and I've already got that. It's 63.02. And so the mass that is going to be expected is 63.02 grams of the HNO3. Okay. So there we go. We've done A, we've done B. Now C. C says, what mass in grams of the excess reactant remains at the end of the reaction? Okay, so this is kind of cool. So we know that this hydrazine, or the N2H4, is excess. We know that it's left over. So how much of it is left over? How much of that 120 grams is left when the 120 of the H2O2 runs out? Well, look at this. Again, we've already done a lot of our steps, and I'm just going to show you this. I'm going to go to purple here for a second. So what I want you to do is to really, again, still ignore all of this information. We're going to ignore, pretend we didn't know that. And what I'm going to say to you is, let's go to step 3 again, but this time we're going to compare the H2O2 to the N2H4. So watch this. I'm going to do another step number 3 of stoichiometry, but I'm going to compare the H2O2 to the N2H4, So the mole ratio, look at 3. The 3 I've put there tells me I'm redoing step 3. So it's a 7-to-1 ratio. It's a 7-to-1. And the amount I have, look at this, the amount I have of the hydrogen peroxide is 3.53. So 3.53 to X. Cross multiply, here we go. So 7X is equal to 3.53. And so divide by 7, isolate the X, and basically you can see that we're going to end up with roughly 0.5, so 0.5 moles. So this is interesting. So then if I use up all of this 3.53 moles of the H2O2, which I knew was limiting, I will also use up 0.5 moles of the N2H4. So now look at this. I am going to go back to my step 4. I'm going to go to another step 4, and I'm going to figure out the mass of the N2H4 that will be left. So I'm going to, actually, what I'm going to do is the mass that I'm going to use. So it's N times capital M. It's 0.5. I go back to the molar mass of N2O4, which was 92.02. So 0.5 times 92.02. And look at that. I used 46 grams of the N2H4. That's the amount of N2H4 used. So as that H2O2 was running out, I was running out. Eventually, the 120 grams disappears. It's done. At that point, I've used 46 grams of the N2H4. So the amount left over, therefore, the amount of N2H4 left over is the original amount, the 120, minus the 46.01 grams used. So, and you get roughly 74 grams are left over. The amount left over is the 74 grams. Okay, so that's a tough question. It asked a lot. You know, it asked you have to identify the limiting reactant, then you had to figure out how much of a product is produced, and then come back and figure out how much of an excess reactant remains. Good luck on your homework, and we'll go from there. Take care.